Okay, so um, for today, I will finish the chapter 7 techniques sections for partial fractions. If we have time, I will continue still chapter 7. We still have the improper integral, and if we still have time, we can move to approximations. But I think maybe approximations next Thursday. But um, because we still have today, next Thursday, next week, and then next 2 weeks, and after that it will be the final exam schedule, right? So according to the our schedule for quizzes, we should have at least one more quiz. So I think the possible schedule is next week, so that the next 2 weeks you can review for your final exam preparations, right? So next week we will have a quiz, chapter 6. Okay. Chapter 6 will include the area between curves, the volume, and then the last one will be the average value of function. Okay. So let me write here. So quiz 4. Wait, a little bit delay. Okay, so for quiz 4, it's chapter 6. This is area between curves. Volume or solid revolution. And then average value. And volume, you have the disk method and the shell method. Okay. So next week, Tuesday next week, okay? Tuesday is 29. Okay, December 29th, the quiz 4. And also, for your final, I want to prepare some schedule for you, because this final will be started from 11, right? January 11. Let me write the dates first. 13, 14, 15. Okay. Uh, do you have the other classes scheduled for final? Not yet. But I think there will be obvious schedule, right, for some of professors, like maybe in Wednesday and Monday, or chemistry Wednesday, right? So maybe Wednesday, right? Maybe Wednesday. And I was thinking, between 14 or 15, Thursday and Friday. So what I have in mind is I have two classes, right? This class and the other class. I want to combine all, so we only need one time in a big classroom. So I want to look for big classroom between these 14 or 15. Okay, but I hope maybe 14. But it still depends on the class. But maybe between these two. Okay, between these two. Between these two. Maybe afternoon. Yeah, maybe afternoon. But if it is only available in the morning, then we have in the morning schedule. I will look for the classroom first. Okay, which classroom that we can get. Okay. Or do you have any suggestion for the day? Any suggestion? 12? 12? Okay. Really? 12? Why? Why? How about your other course, like from your global engineering, or other course like physics, chemistry? Like maybe in what time? Usually it's the same time as the course, right? Different? Okay, okay. Okay, let me check the classroom first. Okay. If, for example, we don't really have the classroom on this 14 and 15, then maybe I will look for another day. Okay. I will look for the classroom this week, so I will announce when I have the information available. Okay. Okay. Now, okay. Let me review a little bit. Okay. A little bit review for the partial fractions. Okay. So the first thing is, if you see the case one here, okay, if the q is the denominator at the bottom, so let's write the r over q. If you separate, become remainder and the quotient. If the q is the product of linear factors and the factor is not repeated, okay, meaning a1x plus b1 and a2x plus b2 is different. Okay? A1 is not a2, b1 is not b2. Okay? So all the linears are different uh, equations. Okay, and the thing is, you can separate it. All the terms becomes each fractions, each rationals. Okay, and you will have at the top only a single constant. Okay, single constant like this. Okay. And the example is, if you have like this whole equation, the fractions, when you can factorize, okay, when you can factorize the denominator, become x and 2x squared plus 3x minus 2. I hope you can see the number. Okay. So when you can factorize and you can make like each factor like this one, you can separate it, the whole, these three fractions in each single fraction. Okay? And the top will be only a single constant. Our job or our works now, we need to find this constant. Okay? And we need to reverse. Okay, we need to reverse. So how to reverse is, imagine this is the multiplication of these three factors. Like when you have, imagine you have like three separated fractions and you want to make all into one single denominator. Okay, what you need to do is you multiply this, and for each value here you will divide the total, divide by this x, and then multiply with a. and the total divided by this 2x minus 1 multiplied by b, and so on and so forth. And we get all the equations here, and this should be equal the original equations. Okay, x squared plus 2x minus 1. And what we are going to do is all these terms we need to group based on our variables here. Okay? It has x squared, x, and then a constant. Okay? So we are solve this first. We simplify the terms. We grouping each with x squared, x, and a constant. We are grouping together. And we get the the equations. Okay, so x squared, you have 2a plus b 2c. On the right side, it's only one. So 2a, b, and 2c. 2a plus b plus 2c is 1. And the other one is 3a plus 2b minus c is 2. And the constant is minus 2a is minus 1. Or 2a is 1. So a is half. And then half you can put here, solve these two equations. We get the b and c. And based on our results, we can change all the a, b, c with our constant, and we can solve them. If we need to integrate them, we can solve them separately, and then that is the final answer. Okay. So this is not the final solutions. Okay, the final solution we need to put back to the integration, and we need to integrate each part. Okay. Okay, that's the case one. Now, let me go through the case two. Okay, case two. Okay. The denominator, or the Q, the quotient, is a product of linear factors. We can also say this is repeated linear factors. Okay, the example, let's just say this is what we call the linear factors. And then plus A2. Okay, so what the repeated linear factors mean? You have a1 x plus b1. Is this the equations? Okay, the repeated linear factors mean you will have another same equations, but it's squared, and then maybe cubed, maybe with fourth, and so on and so forth. But the inside is the same equation. Okay, and you can add them until whenever number you have you will have. Okay. For example, um, Let's plus 1. Okay, so from this case 2, notice that the top one, okay, the equation on the top, is always a single constant. Okay, it's always a single constant because you will recognize the bottom parts is actually linear equations. Linear equations. Okay, it's linear equation, but it can be squared, it can be cubed, but still it is basically the original is linear equation. So if you have these equations here, okay, I can write this down as x plus x squared plus x minus 1 plus x minus 1 squared plus x minus 1 cubed. And then the top will be, let me write as A, B, C, D, E. Okay. So this is called the partial fraction. I think this should be, I think in high school, as high school, this high school, right? Separated like this. You see, x squared here. The maximum is 2 here. So you need to start with x1, x2. So if you have x cubed, you will have x squared, and x cubed. Okay. If you start x minus 1 is cubed, you will start from x minus 1 with power of 1, x minus 1, power of 2, and then power of 3. Okay. If you have 4, then you need to add 4, and when you have 5, you add 5. Okay. Okay. So the rest of the solution is the same as before. So we can compute the A, B, C, D, E and make it equal to the left side here. And we will get the A, B, C, D, and E. Okay. Let me write a little bit. Yeah, you have this, and all these equations need to be equal with the x cubed minus x plus 1. And you see, it doesn't have the x squared, right? So anything that you will get in x squared when you're grouping x squared will be 0. Okay, and if you get a single constant, it will be equal 1. Also, the x cubed is 1, and for the x will be negative 1. Okay, I think x minus 1 cubed is still doable. You will have 1, 3, 3, 1. This is also same. Yeah, I think I will leave the rest to solve. Okay. Let me give you maybe a little bit easier, not including the cubic parts. Okay. So another thing, okay, why this important to have the repeated linear factors, okay? Actually, if you think first, maybe you will only have like 1 and 2, right? Separate become 2. But if you have 2, you still have x squared. The top will be ax plus b, right? Let me write for you. If you think this is becoming 2, if you have x squared here, you will have ax plus b here. Okay? And this will be x squared c plus dx plus e, right? How many constants you will see? A, B, C, D, E, right? Okay. If we see here, we also have A, B, C, D, E, right? So actually, this is a really nice case, okay? So if you're having this is also doable, but it would be helpful if you can really divide all into a single component, okay? If you divide all, like you have these 5 partitions, right? You have 5 partitions of the fractions. You will have really nicely a single constant on the top on all 5, right? Rather than this. Okay. And this is actually, if you simplify, it will getting to that terms. Okay. So this repeated linear factors is, I think, one easy solution to solve the, if you have rational functions, polynomial, and you can reduce the terms. This is one of the best solutions, okay, using the partial fraction. Okay. Okay, maybe an actual example that we can solve easily. Okay. Now it seems so scary, right? It's like large, huge, large integrations, and you have like uh, high degree polynomial functions, right? But if you think deeply, okay, the top equation is x to the 4. The bottom one is x cubed, right? So if you think only the x to the 4 and x cubed, you will have at least x, right? So you can reduce these fractions into simpler forms. It's easier than the top one, the previous question. It's easier. So first you can do some long division in polynomial, and you can reduce the form. So you can do long division. Or, okay, uh, if you uh, like, maybe if you want to, like you have the x4 minus 2x squared plus 4x plus 1. Okay. And divide by x cubed minus x squared minus x plus 1. Okay. If you are writing this in your paper and maybe you are thinking, oh, it's really long, maybe I will make some mistake. like, or maybe, okay, I was too lazy to write it all down. We can check, okay? We can check first. Check if we plug in here, we can check the bottom part, okay? We can check the bottom part here. Check, okay? Check. Let's just say x is equal 1. Check the solution, 1 minus 1 minus 1 plus 1. Is it 0? 0, right? So meaning x equal 1 is our factors, right? And then we can use the syntactic division. Let me write in the, so maybe checking the Q1, okay? So let me write completely. So x equal 1 is a factor of qx. And then the qx, I will start the qx first because I want to, so first to solve this, you need to think the q can be factorized, okay? Because we already did, okay, it can be factorized. So we can write 1, negative 1, negative 1, 1. And then we can write 1, x equal 1, okay? And then solve this. Okay, it's 0. Okay, that's already correct. Okay, it's the x equal 1 is a factor. Then we can write the factor is x minus 1, and then x squared minus 1. Okay, the factor. And x squared minus 1, we can factorize, become x plus 1, x minus 1. And we can write this as x minus 1 squared x plus 1, right? Okay, now, oh, I think you still need to go for long divisions. Let me move this. So x4. But I think it's not bad. And then plus 1. I think it's not really bad. So it will be x cubed. It's nicely canceling most of the variables, right? So we still have 4x. So let me write yes, 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 yes. Okay. Okay, then we can write this as x plus 1 plus 4x. Okay. And in the bottom, we can write x minus 1 squared and then x plus 1. Okay. Now, x plus 1, we can easily integrate this. Okay. Our focus now is on this 4x, x minus 1 squared, x plus 1. Okay. So let me write this as a new equation. At least three partitions we will have. And it will be x minus 1, x minus 1 squared, and then x plus 1. Let me move to right. Okay, so we're actually getting a nice number here. Okay. It's not too complicated if you can separate this. Okay. Now the idea is the same. We need to look for A, B, and C. Okay? And notice that I didn't put my integrations here. Okay, so that will be my final process. Okay, so to help you just focus on separating all the partitions, making each fractions, each rationals, and then at the end, then we can add integrations. Okay. So this is just to help you to focus, okay? So sometimes when you are dealing with integrations, you are thinking which method I need to use, right? So my suggestions is if you are if you want to focus on rewriting the form, okay, you can just ignore the integrations first and focus on the form, what kind of form you want. Okay? Because sometimes you want to integrate immediately, but it's resulting maybe not really a good process in your mind. Okay, so better if you just ignore the integration first and focus on the form inside of the integration. Okay, so you have the A, B, C. So we can write this. We can divide this to each of the denominator of A, B, C. We get the A is x minus 1, x plus 1, plus B, x plus 1, and then plus C, x minus 1 squared. And this should be equal 4x. So the other terms will be 0. The other terms will be 0. So let's just multiply all. And let me write this as x squared minus 1. Okay, and I can write this as x squared minus a plus b plus c is equal 4x. So b minus 2c is 4. A plus c is 0. So a should be equal negative c. And negative a plus b plus c is also 0. This will be starting the 2c plus b is 0. And I can solve this negative 2c plus b is 4. So we can add this both. So 2b is 4. So b is 2. B is 2, then 2c plus 2 is 0. So c is negative 1. And a is 1. Right? A is negative c. Okay. So we get all this. Okay. So we can write the a is 1, b is 2, c is negative 1. Okay. Okay, this is you need to write this. So whenever you have the linear factors, okay, it will, despite the process is actually very long, uh, like you need to write the long divisions, and then you need to write the repeated factors, and then you need to integrate. Okay? At least three process you need to have. But the repeated linear factors will play nicely, and you will have really good solutions in your final answers. Okay? It will be different if the linear factors is not repeatable. That will be or the factors in the qx is not reducible. So you need to write, like for example, x squared um, plus 4. You need to write x squared plus 4. Right? You cannot factorize in any way. Then that will be different case. Okay? But here it really plays nicely. Okay? You'll get easily a single constant on top every fraction. Okay? Let me write the final solutions. So let me remind you the questions is x4. This is the same questions. I'm just rewriting and make the final solutions. This will be integrations x dx plus dx plus 1 over x minus 1 dx plus 2 okay, dx. Okay, and then we can solve separately. So half x squared plus x plus ln x minus 1. And then this is actually the same as x minus 1 power of negative 2. We can integrate that, become negative 2 x minus 1. Yeah. And then minus ln x plus 1. You can plus c here. Actually, this is already done, but if you want to be more simplify in your solutions, you can combine the ln. And depends on maybe if you see the question have the options, you check the options whether it's correct or no, or you need to write in another form. Depends on the question. But I think up until here it's already finished here. Okay. Okay. Okay, we move to the case 3. Okay. Case 3. The QX contains irreducible reduce none of which repeated. So it's not repeated. So QX it contains irreducible factors. So you cannot reduce the power. Okay. So if the QX is in the quadratic, let's say x squared plus bx plus c, whenever you have p squared minus 4ac less than 0, meaning it will be a reducible factor. So we need to write ax plus b over ax squared plus bx plus c. So for example, so you have at least 3 partitions. It will be x minus 1 and x squared plus 1, x squared plus 4. And this will be a, and this will be bx plus c. Okay. And this is dx plus e. And we need to write down the factors in terms of the whole linear. Okay. Because this is the irreducible factors. Okay. X squared plus 1, x squared plus 4, we cannot factorize anymore. Okay. So we need to write the top bx plus c, bx plus e. Okay. I think for x minus 1, if you integrate, you can get easily ln, right? How about this one? This two. If you integrate, what will happen? How to solve? Maybe just ignore this part for now. Okay? Just make maybe any constant here. Okay, any constant here. If you have like x squared plus 1 at the bottom, how can you solve? I think for this the middle one is easy. If I have 1, what is this? Tangent inverse, right? Arc tangent, and then plus c. What if I have this? Hmm? Yeah, but it will be like longer. This actually, if you see the pattern here, is 1, okay, x, okay. Let me get you uh, into the derivative part first, okay. If I have the first derivative of tangent inverse, right? This will be 1 over 1 plus x squared, right? Okay. If I have 2x, I need to multiply by 2. Yes, 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 yes. But we can also just using the property of the tangent inverse. So if I have let's say tangent inverse of x over 2, it will be, or let me write here, it will be 1 over 1 plus x squared over 4, right? And then you need to multiply with half. solve this, and what? 4 4 over 4 plus x squared is true. 2, 2, 4. So it's become 2, 4 plus x squared. Okay. What is our form here? It's only 1, right? So we need to multiply with another half. Okay. From this, I can write. Okay. From this, I can write this is 1 over a tangent inverse x over a plus c. Okay. If you forget this, do what I did, because I also forget this often. So you can write this and then reverse the derivative, and then you get this expression. Okay. Okay. So let me review a little bit. Okay. So if you get this, you can separate this, become bx over x squared plus 1 and plus c x squared plus 1, right? I think for this one, um, this will be play nicely with substitution. Okay, this will be easy to solve by substitution, and this will be solved by the tangent inverse. Okay, and usually this is most of the case for this type. Okay, you need to use the tangent inverse. And if you have like maybe it's not x squared plus 1, maybe 4, maybe 9, or maybe any number that can be here. You just need to square root that number. Maybe if this is 5, then you need to square root 5. Okay, it will be having a square root 5. Okay. So if you have, like, for example, plus 5, you can go directly 1 over square root of 5 tangent inverse, and then x over square root of 5 plus c. You can go directly using this formula. If you forget the formula, you can did what I did, and then play with the terms inside the tangent inverse. Okay. The other case, okay, uh, case 4, this is the last case for the partial fraction. So case 4, Qx contains repeated. Okay. So now we have repeated, but it's irreducible factors, not linear. Okay. So if Qx has a factor, let's say this quadratic functions with power of r, and b squared minus 4ac is the same, less than 0, meaning it's irreducible. Then we will have A1 x plus B1. Okay. So actually, the partial fractions, the idea is if you have the uh, repeated linear factors or irreducible factors, you simply treat both of them similarly. Okay. What you did is just add, if this is quadratic functions, this should be the linear equation, ax plus b. Okay. So let me just give you the example. Okay, maybe this is the example. Okay. Now you'll have 1, 2, 3, 4, 5, 6, 6 partitions, 6 fractions. Okay. And whenever your fractions have quadratic at the bottom, the top one, the top equation should be ax plus b. Okay. The linear equations. Okay. Let me just write this. Let me write on the bottom. Okay. So a over x plus b over x minus 1, and then plus this is no, cx plus t, and it's x squared plus x plus 1. Okay, and then plus ex plus f. This will be x squared plus 1, and then plus this is gx plus h, and then the last one, the cube. Yeah. So uh, the important thing in the case 4 is you will have some quadratic equations at the bottom, at least the polynomial. And if the I think for our course, we will not have the cube. Okay, at least maximum is the quadratic. Okay, if this is the cube, then this will be the quadratic, and that will be troublesome. It's difficult. So this will be the quadratic functions, but this quadratic, it can be also repeated. So if it's not factorizable, it's not if it is irreducible, you cannot get any factor from this one. Then you can write this as it is. Okay, and then if it is repeated, like x squared plus 1, and then until the cube, then you write and treat them as the linear repeated factors. But the top one should be the linear. Okay. So if this is quadratic, this is linear. Okay. Linear. Okay. Okay. So what if, okay, what if this x may be having cube, okay, then you need to add 1, 2, 3, single constant, single constant, single constant, x squared, x cubed, okay? And if you have x minus 1, for example, it's squared, then you need to have x minus 1, and then the other one, x minus 1 squared, and it becomes longer. Yeah. But that's just example, just an example. Yeah, just an example. Even I don't want to solve this, it's too long. It's too long. Okay, any questions? I think you don't need to memorize like we have 4 Ks in the partial fraction. No need. It's it's really boring, right? It's easier if you just look at the if you just look at the form, okay? So if you like you have px and qx, okay? The question is, can you factorize the cube? Okay? The questions factorize or irreducible. This is just uh, a think, okay, a thinking to solve the partial fraction or the rational function in integration. So this dx, right? So if this is factorizable, then you need to factorize maybe x minus a, maybe x minus b, okay, or maybe x, okay, or sometimes, okay, sometimes like what we did before, maybe it will be like you have it squared, okay, maybe that, or you will have another terms that say that okay, we have x squared plus c, and we cannot do anything here for the qx. So you will have 1, 2, 3, 4, at least 4. The first one is x minus a squared, x minus b, and then x squared plus c. But here is a, b, c, and this one will be dx plus e. And then it can be also, like if you have this squared, it can be also here. Then you have to add more fx plus g, and then this will be x squared plus c, and then squared. Okay? It's not too difficult, right? Not too difficult, right? So all the things is just compiled into this one way of thinking. So sometimes when you read a textbook, okay, sometimes the textbook is really strict with the terms in English. Okay? In English terms, they will strict like the formula, the rules. They was officially really, how to say that, rigid. Like maybe you have uh, some barrier in your mind, like okay, I'm not understanding all of this. But if you are looking at another perspective and make it in a flexible way, you can make anything in the textbook much simpler than we thought before. Okay? So if you have the textbook, okay, my suggestions is when you read the textbook, you need to also try to write down some notes on your own, okay, and then try to understand what you are reading, okay? Because sometimes it have like long definitions. It is correct, and it needs to be written like that because in math you need to have like exact definitions. But maybe you need some analogy, some visual So you need to have some help. Uh, the Wolfram Alpha is good example for your solutions. Okay, Wolfram Alpha or GeoGebra. Okay. I'm always um, depending on these two myself. Okay, depending on these two. Whenever I saw integration, saw a derivative, I go to the Wolfram Alpha first to check any solutions and any alternate solution. And to check the visual, I go to GeoGebra to check the visuals. Okay. And you can also write down the partial fraction in Wolfram Alpha, but maybe long typing. Okay. So this is the whole partial fraction what we did these past weeks. Okay. Okay, now I want to give you some practice on the chapter 7, especially the techniques. And then after some practice, we can move on to the improper integral or maybe the approximations. Have you learned this secant x dx? This class? I forgot. Not yet. Not yet. Okay, can you try secant x? The clue is you need to think from yeah. Can you try? Have you get it? Finish. I think it 2 more minutes. Okay. 2 more minutes. 2 more minutes. Okay. Secant. It will be very difficult to solve. Okay, I'm giving you this the derivative of secant and derivative of tangent as secant x tangent x and secant x squared x because okay, if you see secant x only secant x, okay, I see this form. It has secant x, at least has secant x, right? So the idea to solve this is actually quite tricky, and the idea is to manipulate the secant into another form. Okay? Let me write something to remind you that we can also write some. Okay, now the idea, secant x, I need to multiply secant x with another fractions, okay, so that I will get these results. Okay. Or let me just write, if I'm having these two together, I can write if I'm plus add both this together, I will have this, right? At least this. So maybe I can add this secant x plus tangent x and multiply with the secant x. Can you think any clue from there? You get it? No?